Okay, so let me welcome you to this 11th lecture of our course on reinforcement learning at ASU. And today we're going to talk about minimax problems, where in addition to the controller, there's an adversary who chooses a counteracting control with the aim of maximizing the cost as we try to minimize it. We'll argue that these problems are difficult to solve exactly, like one-player problems. They're much more difficult, in fact. Then we're going to discuss approximations, in particular Minimax rollout. And then we're going to discuss about a new method that we haven't presented before in this class over the years, was developed over the last year, and it involves approximation in both value and policy space, where we approximate the adversary with a nominal adversary with a known policy. And then the problem becomes one that can be solved by one-player methods, MPC in particular. And we're going to discuss the application of this idea in computer chess and some other contexts. So here's the outline. We're going to talk about adversarial problems in general with sequential decision-making by a controller and an adversary. And we're going to see how the solution can be obtained by dynamic programming exactly. And then we're going to argue that this is difficult, and we're going to consider approximation in value space and rollout. And then this will take us half the lecture. In the second half of the lecture, we're going to discuss about this idea of approximation in both value space and policy space, talk about computer chess with MPC type of methods, and then discuss linear quadratic problems, which turns out to be another favorable class of problems, and we'll see how this idea of a combined approximation value and policy space works, and provide us with an example to appraise this method. So let me introduce minimax control problems. Other names that you'll see in the literature is robust control, robust in the face of uncertainties. Or an older game is games against nature. So we have disturbances, WK, as usual, but we adopt a worst case point of view, and we assume that the disturbances, WK, are chosen by an adversarial and omniscient, knowing everything, decision maker. And we try to do the best, assuming the worst responses on the part of the adversary. Mathematically, instead of having a probabilistic description of WK, we assume simply that it belongs to some set, a set membership description. And in particular, the system is what you see here. WK is a disturbance that is not stochastic anymore. Instead, we just assume that it belongs to some known set that depends on XK and WK. I'm showing here the case of a finite horizon and time-varying system, but there's also everything I'm going to discuss applies also to infinite horizon with a few modifications, and also with a stationary system. So I'm going to give you the dynamic programming algorithm for this problem, which is to find a policy. A policy as you know it, a sequence of functions of the current state that satisfies a control constraint, and one that minimizes this cost function. So the cost function of a policy starting from an initial state x0 involves plugging in this policy and also taking into account the disturbance WK, which is now not random. So this is not a random variable, it's a number, and we try to maximize, and we consider as cost the maximum over all possible numbers W. In other words, we try to minimize this, assuming that the W's are going to be chosen by maximization subject to the constraint. So this is a well-defined number here J pi is a function of the initial state, a value function. And what we're trying to do is minimize overall pi. The best way to think about these problems is everywhere where you used to see expected value, now place maximization, okay? That's and then everything matches. In particular, the dynamic programming algorithm, by replacing expected value with maximization, is like so. Start with some terminal condition, the terminal cost. We go backwards to jn minus 1, jn minus 2 star, and so on. And we obtain this by mini-maximizing over u and w. First with respect to u, and then w, knowing u, maximizes, okay? So if we had expectation here instead of maximization, it would be exactly the same algorithm as before. And its character is sort of similar. We have enormous computational difficulties with large state spaces, storage, difficult computations, long computations, and so on. Generally speaking, this algorithm is just as infeasible, if not worse, as its expected value counterpart. So you can't hope to solve problems in general using this algorithm, and it's only toy problems or some problems with very favorable structure that can be solved with this algorithm. So it is natural to consider approximation in value space, whereby we replace J stars by J tildes, some functions that we somehow design by training, by heuristic choice, by whatever. And then the problem becomes, at each state, xk, we have to solve this minimax problem, but involving a single stage. This is one step look ahead, right? It involves a single minimax problem with a known value of J tilde. So that would be the approximation in value space approach. And it's the same as what we had before. In place of expected value here, you have a maximization. So this is all similar to the stochastic case, but there are some further difficulties when you compare to the stochastic case. Can you see a difficulty here? If I had expected value here, and I compared it to having maximization, which one would be easier, you think? The expectation can be done by simulation, right? Maximization requires you to solve an optimization problem, which is harder. So simulation is out in these problems. That's a big difference in reinforcement learning, where you rely a lot on simulation, right? There's also some mathematical difficulties, namely, the expected value operation is a linear operation. In other words, expected value of a sum is equal to the sum of the expected values. That's not true with maxima. And that creates analytical difficulties that, down the line, they create problems. So Monte Carlo simulations are unavailable, and in particular, rollout is affected quite a bit, right? Because rollout for stochastic problems involves policy evaluations using simulation in many cases. So we have to rethink rollout within this context. So let's take another angle now. There's a branch of optimization in mathematics called game theory. Game theory is very fundamental in many contexts, including economics. For economists, game theory is a very, very fundamental theoretical framework. And minimax control and game theory are related. And some of the methodology for minimax control is related to methodology for zero-sum games. Now, zero-sum games involve, again, two players and a cost function. One player, the U player, aims to minimize the cost, and the other player, the W player, aims to maximize the cost. However, there is no special preference given to the minimizer versus the maximizer. We view them as equal, and we consider two minimax control problems. One is the min-max problem, where the minimizer chooses policy first, and then the maximizer chooses second with knowledge of the minimizer's choice, okay? So this is more unfavorable to the minimizer because he reveals his play to the maximizer before the maximizer makes his choice. Now, the max-min problem is the opposite. The maximizer chooses policy first, and the minimizer chooses policy second with knowledge of the maximizer's policy. So that favors the minimizer and handicaps the maximizer because he has to reveal the policy, his policy. And generally speaking, because of this asymmetry, you have the max-min optimal value is less than the min-max optimal value or equal. Max-min less than min-max, okay? That's the first thing you learn in game theory. On the other hand, in game theory, you are particularly interested in situations where the two are equal. There's an equilibrium, and it doesn't matter who plays first or who plays second. So that's the theoretical focal point of game theory. Find conditions and problems that guarantee that the max-min value is equal to the min-max value. And there are some fundamental results here that predated a lot of optimization theory, by the way, by von Neumann, and there's a famous book that was published in the 40s, The Theory of Games, by von Neumann Morgenstern, and that had a lot of influence in economics as well as in optimization. Okay, so that's the connection between min-max control and zero-sum game theory. Minimax control deals with half the problem that game theory deals with. Generally speaking, the equilibrium condition, min-max equals max-min, is unlikely to hold in problems that are of interest to us. In reinforcement learning, where you try to make sequential decision, you try to do sequential decision-making under uncertainty. On the other hand, there are some exceptions, and I will single out two exceptions that are relevant to our sequential decision-making context. One is discounted Markov games, and dates back to the 50s. And here we have a Markov chain that is controlled by two players, the minimizer, who chooses U, and the maximizer, who chooses W. And there's a finite number of states, finite number of controls. There's a discount factor. There are transition probabilities that you know, and there are costs that also depend on the current state I, the next state J, and the player's choice. Now, one difference here also is that the players are allowed to use randomized policies. Instead of U and W being single choices from a finite set, they are chosen to be probability distributions over the corresponding player's controls. So this is a probability distribution over the minimizer's set of choices, and W is another probability distribution. And the choice of this randomized policies equilibrates the problem, makes min-max equal to max-min. Okay, that's a fundamental result in game theory, that in order to get min-max equals to max-min, you have to have some kind of randomization. And I can't get into this some more. I just want to make you aware that there is the analog of discounted MDP problems. There's an analog in Minimax land, which admits the standard results. Bellman's equation, optimality conditions, value iteration. An important complication is policy iteration. The policy iteration algorithm in this context is more complicated, and does not quite converge always. There are some theoretical difficulties, but the algorithm can be modified to make it work. And there is a discussion in the textbook and also references to look further into it. The problem here is, okay, I'm going to be very glib about it, but remember in Bellman's equation, the Bellman operator was concave, and that made a lot of difference in terms of our pictures being workable. On the other hand, in min-max problems, the Bellman operator does not have a concave graph, but it has a concave and convex simultaneously graph. And that creates difficulties with Newton's method, for example. Newton's method does not converge globally, or does not converge, has to converge only within a certain, converges only within a certain region, restricts the region of convergence of Newton's method, and creates these problems, including the problems that have to do with policy iteration. Okay? Now, all of this is interesting mathematics, and for those of you who want to get more into this, might be useful material. On the other hand, still in this course, we're interested in approximations. We're not interested in exact policy iteration. We're interested in approximations. So perhaps this theory is of tangential interest to us within our reinforcement learning focus. Okay, now the second exceptional min-max problem is linear quadratic, the analog of linear quadratic problems. So remember linear quadratic problems, Riccati equations, linear policies, are framework for approximation, value space, and illustrating Newton's method. It turns out that if you introduce the extra opponent, the W, in a linear quadratic context, a lot goes through. In other words, there's still a Riccati equation, there are still closed form solutions, there are linear policies, everything works through with some difficulty and with a few additional conditions that I'm going to discuss a little further in the class near the end. So again, here we have a linear system. We have a quadratic cost for both players. There's a closed form solution. And I'm going to show you this closed form solution near the end of this lecture. So these are the two exceptional problems, but from the point of view of reinforcement learning, they're not all that interesting because perhaps as a source of inspiration, but not as a source of solution methodology. Are there any questions so far? So we'll now turn to approximations and things like rollout. First, approximation in value space. Remember, approximation in value space involves at a current state xk, looking one or multiple steps ahead and replacing J star with J tilde, which encodes the cost of the future starting from the state at the end of the look ahead. So L step look ahead, cost function approximation to encode the future. However, instead of expected value over the W's, we have maximization. So what do we have here? At state xk, we have to solve over these controls of the L steps this problem, which involves maximization over the W. This was an expected value, but now it is a control problem, a maximization problem over the W's. that involves an L-step horizon. It can be solved by one-player dynamic programming for each U and mu k and so on. And that's what this involves. Now, any cost function approximation J tilde is permissible here, as before. And you can think of obtaining J tilde by offline training or by other methods, heuristic methods, rollout, problem approximation, everything that, all the methodology that applies to one-player problems can be modified to work within this context. Remember the three approximations view in approximation in value space. There are three approximations. One is the J tilde approximation. The other one is the minimization approximation. And the third one was the expected value approximation. That corresponds to approximating this maximization problem with some suboptimal solution. Okay, let's consider now finite state problems. This L-step minimax control problem can be solved by dynamic programming over a minimax tree of states and subsequent states. In other words, you start at state xk, you apply the control u, that gives you that takes you to an intermediate state, and then you apply a control W that takes to additional state. So you construct a tree of moves and counter moves, and you solve over this tree with dynamic programming, the minimax dynamic programming. Okay, we've talked about L-step look ahead through a tree search. We've discussed the selective look ahead, incremental pruning. We select forward dynamic programming. All of these are applicable with some variations to account for the maximization. And now in minimax problems, there are also some special techniques, in particular a technique called alpha-beta pruning, which you may have heard in algorithms courses. And alpha-beta pruning facilitates the minimax search over a tree by pruning parts of the tree that are entirely unnecessary. And now this is not a heuristic, this is not an approximation. Alpha-beta pruning does not throw away anything. It gives you the same optimal value as without pruning. So this is a good technique to apply always, as far as I can tell. And in fact, it's very important in computer chess and in game problems. In two-player game problems, alpha-beta pruning is used always to accelerate the solution of these problems here. So this context is representative of the algorithm that people use for most two-person game programs for online play. Online play selection of U at any given state, including chess. In chess, the state is the current position. U is the choice of the player. W is the choice of the opponent. And typically, we look forward over a tree and use a position evaluator at the end and find the move at the current position. And the opponent plays, and we do the same thing. This is a representative example of approximation in value space for minimax control. Now let's talk about rollout. Rollout is the special case of approximation in value space where J tilde is chosen to be the cost of some base policy. The cost function of a base policy that corresponds to the next state. Here I'm talking about one step look ahead, and also the choices of the W's from the next state up to the future. Now, in expected value problems, in stochastic problems, here we had an expectation, and we just run the the base policy using simulation and calculated this expected value here. Now, here we have a different situation. Instead, we have an optimal control problem. It's a longest path problem, a maximization problem if you use this G as the cost of some link in a graph. This is a longest path problem with the control variable being the W's. So how would rollout work here? At the current state, for each possible control, okay, for every U, we compute the Q factor of the base policy. The Q factor is given by this formula. It's this expression here. And instead of computing the Q factor by expected value, by simulation, we have to use a maximization, which is a longest path type of problem. So that's the definition of rollout with one step look ahead. Look at all possible choices, compute a Q factor, and then select the control that has the minimal Q factor. That's a rollout control. Any policy can be used as a base policy. In order to have sequential consistency, you have to use a legitimate policy. These issues of sequential consistency, sequential improvement arise also appropriately modified within this Minimax context. And sequential consistency implies cost improvement by the same kind of argument that we have used before. And there are also many variants of this. Truncated rollout, where you consider this cost function of the policy not all the way to the end, but up to a certain limited horizon. Simplified rollout, you throw away some of the Q factors and as being unlikely to be relevant. Fortified, where you use, okay, you remember fortified. Constrained, certainty equivalence approximation, where in here you do maximization over only the first WK, but then you use some fixed values to approximate the maximization of WK plus 1 up to WN minus 1. All of this applies appropriately modified. So I'm going to leave it at that. Are there any questions here? Okay. So now here's a question. How do you find J tilde, okay, in Minimax problems? And in particular, we had a lot of offline training algorithms for one-player problems. How do they extend in Minimax and max-min problems? Okay. Suppose that we have the policy of one of the two players, either a minimizes policy or a maximizes policy. We can improve the policy of the counterpart by using a standard policy iteration approach. So assuming a fixed policy for the opponent, we can improve the other player's policy. So we can do one policy improvement at a time, but can we improve both policies simultaneously? Well, the answer is unclear. In practice, often this seems to work often. In other words, you assume a given policy for maximizer and minimizer, and we do a policy improvement by mini-maximization. That will give us a pair of policies, which hopefully will be improved. Is that true that's going to be improved? Well, it's not clear. There's no reliable theory on this question. Sometimes it works, sometimes it does not. Let's take a symmetric game like chess. In other words, a given position from the point of view of the maximizer and the minimizer is evaluated using the same criteria. And the algorithm for choosing a move is the same for both black and white, right? And similarly with symmetric games of like chess. So we don't need to train a different policy for the minimizer and the maximizer. We train a common policy for both. So can we do that by policy iteration? Well, the answer is perhaps, but not always. And in fact, there are examples where this does not work well. I've been puzzling this question for 30 years, since the 90s, but a couple of years ago, there was a paper from some group from Berkeley, and they constructed an algorithm to spoof an AlphaGo lookalike, okay? Trained the game, a Go game. The program is called CadaGo. So they used this CadaGo to train itself to generate a policy for both the minimizer and the maximizer. And then they played that program against themselves. And they chose a particular sequence of moves that the common policy had not foreseen. And they could beat this AlphaGo lookalike very easily. So that's a case of failure here. And these examples are real. Are they frequent? Not very frequent, but yet they exist. So the conclusion here is that there are no reliable methods for doing training in min-max problems. And what we are going to do next is to consider a different approach, whereby instead of having the adversary, the actual adversary, we will introduce a nominal adversary, which is a fixed but very skilled adversary in place of the true adversary. And then we will train against this adversary by using one-player train methods like MPC, okay? Replace the actual opponent with a nominal opponent, which somehow we're going to figure out what it would be. So that's going to be our approach. And this will convert the Minimax problem to a one-player optimization problem, which can be dealt with the methods that we have been using so far. All of this is new. It has been developed in the last year. And we are going to apply this methodology to computer chess and also another context once we come back after the break. Okay, so let's get started. We're going to consider now an approximation in value space approach where there's an additional approximation in policy space, whereby the opponent, the maximizer, is approximated by a fixed policy. So our motivation now is to address the difficulties of minimax approximation, value space, rollout, and policy iteration. We mentioned those. There are all sorts of problems that can occur, counterexamples, and also the great difficulty associated with these maximization problems. If we didn't have to do these maximization problems, then both in the rollout and approximation value space, then things would be much easier. So that's what we're going to do. We're going to replace the maximizer with a nominal opponent, which is a known and fixed policy. WK is chosen as a function of XK and UK by a known policy. This new here is known, and we're going to call it nominal opponent. Then the system depends on a single player. That's how the system looks like. Depends on the current state on the control, and W is chosen as a function of X and U according to the nominal opponent policy. Similarly, the cost depends only on X and U because the choice of the opponent is determined as a function of X and U by this policy nu. So the problem is a one-player problem, and it can be approached with one-player methods. Approximation in value space, MPC, rollout is much, much simpler. Now, there are a number of issues here that immediately come to mind. how do we determine the nominal opponent's policy, this new? Well, it's a challenge. And you may consider some possibilities, like suppose you know a good policy of the minimizer. There's a typo here. Then you may consider training offline maximization by doing a maximization against some good policy of the minimizer. Other possibilities are heuristics, like you compile a list of adversarial responses to a list of XU scenarios. In other words, you compile a list of critical states and controls and try to figure out adversarial responses that can really make things bad for you. I'm pretty sure they do things like that in designing policies and responses for self-driving cars, okay? They have various adversarial scenarios, like you approach the intersection and there's another car right next to you. What are you going to do? You can construct adversarial scenario and respond to that. Well, there's another car coming in the other direction. There's somebody that's run the red light or things like that. Also, things like blocks on the road, okay? You have to view this as an adversarial response. You view this as a bad scenario to which you have to have a proper response. Another question is, we're using an approximation to the actual opponent by using this nominal opponent. How does that affect the performance? So I'm not going to discuss this first issue here, but I'm going to illustrate it in terms of examples. And similarly, I'm going to discuss performance, how the performance is affected in a couple of examples. The two examples I have are computer chess and also linear quadratic problems. So I'm going to start with computer chess and how you can play better by using one-player methods like MPC. Yes? Of course, you don't know WK, right? But there is an opponent there that chooses a policy that's designed to maximize the cost, make things as bad as possible for us. So we use a suboptimal policy, a fixed suboptimal policy for that opponent. That's what a nominal opponent is, a suboptimal policy for the actual opponent. And I understand if you say that, how do I determine this? Okay, I don't quite know how you do that. But in given situations, there are ideas that pop out, obvious ideas that pop out. And the case of chess, of computer chess, is going to be one of them. Yeah, go ahead.
So based on the condition of the problem?
I didn't hear you.
So based on the condition of the problem we have, so there is no general...
It's problem dependent, yes. Obviously, it's problem dependent. Yeah, there's no general method of doing that, if that's what you're asking. It depends on the problem. Okay, so let's get back to computer chess. Remember that we have viewed the chess position, the current chess position, as the state, the current state. And we have the player's moves are the U's, the choices of control. And then there are the opponent moves, which are the W's. And the way online play goes in computer chess, including AlphaZero, is at the current position, you consider all possible legal moves. Then you consider all possible legal moves of the opponent. And you do this over several steps of look ahead. And you reach at the end at some terminal position, which you evaluate by means of a position evaluator. This is the J tilde, right? The U's, the W's, multiple U's and W's over a sequence of stages, and then a J tilde at the end. Multi-step look ahead with position evaluation at the end. So this is approximation in value space in the minimax setting with finite number of controls and adversary moves. So here is our suggested alternative. We replace the opponent moves with the moves of a nominal opponent, which is a good chess engine, okay? So instead of letting the opponent here choose the moves adversarially, we just have a chess engine choose the moves for us. That's a nominal opponent, okay? Now then, the problem becomes a one-player problem, and it can be addressed with the methods that we know: approximation in value space, position evaluation at the end, and so on and so forth. Is this clear what we're trying to do? The reason this search is hard is because you have these opponent moves, and they broaden, they make the tree more bushy. They make the tree, the size of the tree grows. And moreover, you have this min-max situation. And so we're going to simplify that by using a good chess engine generate the moves of the opponent. It's like we are playing against that engine, okay? And we choose, even though there's an actual opponent that we don't know how he chooses his moves, we assume that there's some chess engine that we're going to play against and choose our best moves, at least within this context of approximation in value space. Okay, so here's our architecture. We're going to use two chess engines as components. That's why we call it a meta algorithm or a meta architecture, using other algorithms as components. And we call this MPC, MC. MC stands for meta chess. And at the current position, we generate all possible moves, and we use a nominal opponent engine to generate the next move. And then these positions here, we evaluate by using another chess engine. So there's a nominal opponent engine, this one here, that predicts the move of the true opponent. And there's a position evaluator engine, which evaluates the position that we get after move and response. One thing to note here is that these moves can be generated in parallel. They can be, the opponent moves can be evaluated in parallel, can be generated in parallel, and the positions can be evaluated also in parallel. So this is not so time-consuming as it seems, okay, if you have parallel computing hardware. So this is our architecture, and we played with different nominal opponent engines and position evaluation engines. They don't have to be the same. And the details of this you can find in this paper, Gundavar, Yichao Li, and myself. And actually, this paper was generated following a term paper by Atharva Gundavar in last year's class. All of this is recent. So I'm going to give you some computational results using engines based on Stockfish. Now, you probably have heard of Stockfish. It's a sort of famous chess engine. It's a benchmark engine, a world champion engine that has developed over decades. And it is the chess engine that AlphaZero beat, okay, in a match. But since that time, Stockfish has adopted some of the tricks of AlphaZero and now probably plays better than AlphaZero. It's considered to be the best chess engine. That's the chess engine that the grandmasters train against. So there are different strengths of this engine depending on how much time you're allowed to let it think. You're allowed to think. And we have tested two variants of the algorithm, the standard version, which is the one that I showed you in the previous slide, and a fortified version based on fortified rollout ideas. And I'm not going to go into this further, but just to say that it plays like fortified rollouts, add some conservatism to guard against the undesirable behavior. It plays a little better against very strong opponents, a little worse against the weaker opponents. And I'll start by showing you the results that we have obtained using against, again, these stockfish nominal opponent and position evaluator engines. With one step look ahead, stockfish is both the position evaluator and the nominal opponent, and we play against stockfish, okay? And we allow stockfish to use different amounts of time to think, half a second. At half a second, stockfish plays a pretty good game of chess. At 2 seconds, it plays a very, very good game of chess. At 5 seconds, it's unbeatable, virtually unbeatable. It just plays almost perfect chess. So we have tested our MPC-MC architecture against these versions of stockfish. And we have tested the standard version of the algorithm and the fortified version. And in one set of tests, we have considered that we know exactly we have allowed the architecture to know exactly the move that the opponent will play. And in another version of the test, we have introduced a randomization, so the move of the opponent is approximately known. And what you see here are the results of 10-game matches. So this is the score of a 10-game match between stockfish of this strength and the MPC-MC using the standard version. And in chess, a win counts for 1 point. A draw counts for half a point, and the loss is 0 points. So 7. Now, in all these matches, our algorithm did not lose a single game. And that's and this was also true of quite a few additional matches, not only against stockfish, but also against the other programs like Komodo Dragon. There are many chess engines that one can have access to. And so, for example, this match here means that our program won 5 games and drew 5 games, okay? Here it won 6 games and drew 4 games, and so on. And what you see here is representative from a large number of experiments, including also other programs. And this is, all of these were with one step look ahead. We can use the architecture of the previous slide in a 2-step look ahead mode or 3-step look ahead mode. The computation per move, of course, increases exponentially with the extra look ahead. We did get some better results with 2-step look ahead. 3-step look ahead, we haven't even tried. It's important to know that parallel computation is essential to reduce the move generation time. And as you look at these results here, you see that against moderate strength opponents, our program wins decisively, okay? So we use the moderate strength opponent as nominal opponent and also as position evaluator and play against it, and we win decisively. That's we have watched this in many experiments that MPC-MC has a decisive advantage against relatively weak opponents of moderate strength. As the strength of the engines increases, then we get an advantage, but not a very big advantage. And at 5 seconds, where stockfish plays perfectly, almost perfectly, we hardly ever win a game. It's always draws, one draw after another, one draw after another. except that once in a while, once every 10 games, once every 20 games, we win a game, okay? And that's what you see here. Here we had to go to a match of 20 games to get a win, to get our first win. So that's what we have observed over many experiments. And the question is, why is this behavior? How can we explain this behavior? We had a hard time explaining this behavior. We had to do a lot of experimentation. And we're still not quite sure why this occurs. So are there any questions here on these tables and on the architecture? Yeah.
How long is the MPC engine allowed to take? But you're varying the stockfish strength, but the computation.
For as long as it took to do the computation. In other words, we tried a little bit of parallel computation to verify that indeed parallel computation helps, but we did not have the full parallel hardware. So it all depended on the implementation that we had. We didn't count this amount of time, okay? If we had a full benefit of parallelization, MPC with one step look ahead would take twice as much, okay? Because there's a nominal opponent evaluation and a position evaluation. So it would take 2 times as much as the ordinary, as stockfish. So we would use 1 second here, 4 seconds here, 10 seconds here. We're not trying to beat the world champion here. What we're trying to do is understand what's happening with this kind of nominal opponent substitution relative to actual opponent. Okay, so here's our consistent observation. MPC improves the play of weak base engines decisively by big scores, and the play of strong world champion base engines narrowly, as I showed you in the previous slide. So the question is, why is this happening? After all, MPC looks ahead only 1 step more, okay? Does 1 step look ahead and then lets stockfish do its own look ahead. So basically, we're adding 1 step to the look ahead of stockfish. And we get such decisive advantages. That's very peculiar. Now here's our experimental observation. MPC plays mostly the same moves as the base engine, stockfish. Doesn't deviate much from stockfish. However, once in a while, it plays a different move. Once every 10 moves, every 5 moves, every 15 moves, it plays a different move. And what's happening here is the base engine misses some hard-to-find strong moves at the first step of look ahead, MPC does not prune at the first step of look ahead. It looks at all the legal moves, whereas stockfish does prune at the first step of look ahead. And occasionally, it may not look sufficiently into some moves that do not seem to be particularly advantageous, but if it were to consider it further, then it would they would prove to be good ones. So, and the reason for this is that it prunes the look ahead at every step of the look ahead. We don't prune at the very first step. We consider all the moves. We do not prove anything. And the important consequence of this is that the first step of look ahead is exact. So MPC performs a true Newton step. Remember the connection of approximation value space with Newton's method. For the Newton step to be valid, there has to be an exact minimization at the very first step of look ahead. The remaining steps can be approximate, but the first step has to be exact. And that's what we see here. And all of this is counterintuitive, okay? Why is it that the first step of look ahead has to be exact and the remainder may not be? And what's the importance of this? All of this is consistent with theoretical the theoretical viewpoint, and the Newton-Steph view. And also, we have seen it in other experiments from other reinforcement learning case studies and MPC studies, where it is very important to have the first step of look ahead be quite exact. So I think that's what's happening here. And it's still speculation because there's no theoretical way to verify this. It's only, theory gives you only a lead into what you should be looking for, and then you have to do a lot of experimentation to verify. But we have done a lot of experimentation, looked at all the critical moves in various games that Stockfish lost, and that's what we found. It missed a move once in a while, and that move turned out to be important, particularly if it's compounded over several moves over a period of a game. Now, here's an important point for you guys that are still considering what to do for term paper. All of this applies to any deterministic two-player game. It applies to Go, it applies to a Chinese version of chess, it applies to any two-person game that's deterministic, not stochastic, deterministic. So if you have a favorite game that you would like to train to test this idea, it's very easy to test it. All you need is to have computer engines for that game. And then you strap them together into an MPC architecture, and then you can verify these observations or add to these observations. And also perhaps get some, publish a paper out of it. So are there any questions here? Okay, so now I'm going to go to linear quadratic problems of the minimax type, where there is a U and a W. And okay, this slide is going to be dense, but it's very similar to things that you have seen before for one-player linear quadratic problems. There's a closed form solution, and the system is what you see here. It's linear, and this is the term. A is a known scalar. It's the linear term in the state. It's a linear term in the minimizer, B1 times UK, and this is the extra term of the maximizer, B2 WK. And we're going to consider cost over in an infinite number of stages. And this is a quadratic cost on the state, Q is a positive number. A quadratic cost on the control, R is a positive number. And a cost on the maximizer that penalizes large moves. Remember, the maximizer maximizes, right? So that's why you see the minus sign here. This term discourages large moves for the maximizer. So if you didn't have this term and that term, it would be exactly the same problem as what you have seen in the past. And the objective is to minimize the cost over U while it's maximized over W. And there's a closed form solution to this. Just as miraculous, this is miraculous. To me, it's miraculous because of the complexity of the problem, but still, there's a closed form solution that, it's very similar to the one for the one-player case. The optimal cost function is a quadratic function of the state. K star is a positive number here, and is the unique non-negative solution of this fixed point problem, which is the Riccati equation, the two-player analog of the Riccati equation. And this Riccati equation has this form here. Okay. If you were to remove the second player, it would be exactly the same Riccati equation as the one that you have seen before. And note that there's a denominator here. And in order for these results to hold, there's some assumption that's needed, namely that the problem data is such that the denominator is positive, at least for the range of values of K that are of interest. There's some assumption here. However, the optimal solution is to solve this Riccati equation, and then the optimal policies are obtained by mini-maximizing in the Riccati equation. Mini-maximizing with this K star, X star being the terminal cost function approximation. Okay, so let's look at approximation in value space with terminal cost approximation K, X star, and both an actual opponent and nominal opponent. In the case where you have the actual opponent, what you do is you introduce this quadratic cost function approximation that depends on K, and you min-maximizing over that at the given state X. Now, the actual opponent is maximizing, is this red that you see here, and there's the red that you see here, and the red that you see here. And if you do this maximization, you get something that's quadratic in X and U, and then when you minimize with respect to U, you can do that in closed form. And this is the result. For a given value of K that provides this approximation in value space, the minimizing U and the maximizing W are linear functions of the state. Is this magic of the quadratics, minimization of quadratic minimization? This maximization maintains the quadratic character of the result. This minimization also maintains the quadratic character of the result, and the minimizing U and W are linear. And the values of this L1 tilde, L2 tilde as a function of the approximation value space coefficient K are given by these formulas. So there's a closed form solution not only to the problem, but also to approximation in value space. However, what we want to do is compare it with the situation where we replace the actual opponent with a nominal opponent. So let's consider the same approximation in value space whereby we replace the actual opponent with a nominal opponent that's of the form L2x. In other words, instead of allowing W to be chosen optimally by the adversary, we replace it by a nominal policy, which is linear as a function of X. So here we don't have a maximizer. We only have the choice of the nominal policy, and we minimize with respect to U here. And this is a linear quadratic optimization, can be done in closed form, and this is the result. The minimizing U is linear with coefficient L1 tilde given by this formula. This is exactly the same formula as for the one-player situation, except A has been replaced by A hat. And this A hat has been influenced by the choice of the nominal opponent's policy, the L2, okay? Otherwise, it's the same. So there are closed form solutions all around, but what we want to do is get an idea of how these two compare, okay? This one, which in general is a pretty hard mini-maximization, with this one, which is a much easier minimization in general. In the context of the linear quadratic problem, all of them are easy to do, but this provides us with a test bed to test our intuition. So I'm going to give you results comparing the minimax policy with an actual opponent with that for a nominal opponent. Are there any questions here? Okay, I have two diagrams, and let me explain these diagrams. What you see here is the minimax Riccati operator. And remember, the Riccati equation is a fixed point equation. K is equal to f of K. So to obtain K star, the optimal solution, I have to find the intersection of this red curve here with the 45-degree line. And K star is at the intersection. So this gives you the optimal minimax cost. And the tangent here can be shown to be the optimal policy for the minimizer. Just as before, you can, in the one-player situation, that's the optimal policy. Now, what we do is replace this minimax Riccati operator with one-player operators, right? Where we introduce different nominal opponents. And what you see here is various curves with different nominal opponents. So in this diagram, we show both approximation in value space and approximation in policy space. Approximation in value space is the horizontal. Approximation in policy space is represented by the different curves corresponding to different nominal opponents. And I have 4 of them here. L2 star corresponds to the optimal policy of the maximizer. And it is 0.22, almost 0.23. And the other values are 0.2, 0.3, and 0.4. And you can see them here, not very well, I'm afraid, but there are these curves. The one that's, and you can see that they're come pretty close to their graphs are pretty close to the ones of the minimax Riccati operator. So they give you policies that are similar to the optimal policy, unless there's a big difference, if you are in this region. If you are within this region, then using a nominal opponent does almost as well as using the actual opponent. And naturally, this one here is the furthest away from the optimal, and the approximation becomes worse. For these others, the approximation is not so bad. Okay. So there's no guarantee that this approach will work, but certainly it's worth trying on your problem because you may be lucky and you may be operating in the good region and you may save a lot of computation this way. Are there any questions on this about this diagram? Yes?
You said this is value space approximation as well. Can you explain how this is done?
Yeah. Value space approximation is we choose J tilde, and the J tilde that we choose here is K x squared, and K is plotted on the horizontal. And the various other curves that you see here correspond to different nominal opponents. That's the approximation in policy space. So choose your K, choose your L, and you get the corresponding Riccati operator, okay? And so what I'm trying to say is here that within this region, the policy that you would get is pretty close to the optimal policy. And so, okay, you have to try to find a good values of approximation value space and approximation nominal opponent that are good. That doesn't relieve you from the burden of trying to find good approximations. Okay, so this is a similar figure. Again, we have approximation in value space represented by K. K star is the optimum, and these are suboptimal values. And we also have approximation in policy space represented by different nominal opponents. And what you see is these curves here that provide you with the actual cost of the one-step look-ahead policy that is generated in response to a given K and to a given L2. Choose the terminal cost approximation, choose your nominal opponent, and this gives you the value of the cost, actual value of the cost. the optimal cost corresponding to the Minimax policy is here. As you change from K star and use the actual opponent, not a nominal opponent approximation, then you obtain this red curve. So this red curve corresponds to approximation in value space, but no approximation in policy space. This is the one that you would like to get close to, but of course, with much less cost, with much less computation, which would be the case where you use the nominal opponent. So what do we see from here? Compare this red curve with the curves, this one and this one, which correspond to values of nominal opponent that are close to the optimal actual opponent. They are pretty close. Now, once you look at this value here, then you see a considerable deviation. And if you consider this value here, which is even further from L2 star, again, there is a considerable deviation between the cost curves. An interesting thing to see here is that, let's take, for example, this curve, which corresponds to a nominal opponent with L2 equals 0.3. At K star, it gives you a worse cost, but if you change the approximation in value space, if you change the terminal cost approximation to some value over here, it gives you the optimal cost. Remember, what the nominal opponent does is it changes the A coefficient of the problem. So if you use, if you were to use the right value of K, you would get the kind of computation that you would obtain from the optimal minimax policy. That's why you see this point here be at the same level as this. And you can see that also with other curves, except for this one, which is way off. So these are all experiments that we have run actually recently just to figure out how good this nominal opponent approximation is. And the conclusion that we come to is that as long as L2 is not too far from the optimum, in other words, the choice of nominal opponent is fairly good, and as long as the approximation is also good, then you obtain a pretty decent suboptimal policy. And what's more important is that the nominal opponent is a good approximation. You can tolerate a lot of error in K, but not as much as in L2. This also comes from intuition. If you look at what's happened, if you look at the equations, if you look at the connections with Newton's method, then this conclusion also, this conclusion is also obtained. It's more important to have a good L2 rather than to have a good K. We hope to get more experience with this kind of methodology. Are there any questions here? Okay, so that's the end of this lecture. Our next lecture is going to be the last lecture of the course. We're going to cover approximation in policy space, like this policy gradient methods, the PPOs, all this stuff that you hear about, which is mind-blowing in terms of how much flawed they are, and also how successful they have been. Okay, this is a tension that I'm trying to resolve in my mind. How can you have bad methods, demonstrably bad methods, work so well on important problems? which proves that you can learn at any time, even at my age. Let me also announce a lecture that I'm going to give in a couple of days, which is for the mathematicians among you. It's a mathematically oriented lecture on the foundations of our course. It has to do with the connections of reinforcement learning and abstract dynamic programming. There will be a video recording of this lecture at the course website by Saturday, most likely. Okay, that's it.